My name is Brian. I'm with the Osborne Company. We have three presenters with us today. We have Albert, who is the president of WaterDrop, and he is going to start the presentation and explain that. He will also be present at the live event, which is what I'm showing on the screen. In a second, I'm going to post a link. If you guys want to register, you can pick which event you want to go to if you guys are going to come. That way we can kind of plan for you. And then we have John Neal with AEA. He is going to be, I should pull up the flyer for the actual event. I got too excited. We have John with AEA, and he is going to be just talking about different heat pumps installations and retrofits that they've seen in the market and some available incentives. And then we have Mischa Egolf with us also. She's with the New Buildings Institute. She's going to be covering information about the market in general also. And there are some multiple initiatives and resources that she's going to be able to put out there. This is recorded, so it will be posted on our YouTube channel after, it'll take me maybe 1 or 2 hours after the actual thing, and it'll be posted on there. So if you guys need any refreshers on the information that you're looking at, I forgot I was sharing my screen. And I am going to pass it off with a little delay to Albert. So Albert, if you want to start us off, we're going to have Albert go first. We're going to have John go second, and Mischa's going to go third. And then, because I always forget to say this, there's a Q&A available, there's a chat available, so please, if you have any questions, type them in there. Because of how much information we're trying to give you guys, we're going to hold off on the questions if I can't answer them directly until the end, and we'll make sure that we get them all answered. Anything that has to be answered after the 1 hour time limit, we'll send it out as an email to everyone. But yes, please, if you have any questions, please shoot them up there as they come up. So yeah, Albert, please take us away.
Great. Thanks very much, Brian. Pleasure to meet everybody today, and looking forward to meeting those that attend a live event in person. That time's coming up really soon. My name is Albert Rooks. I'm president of WaterDrop Systems and its parent company, Small Planet Supply. And so we're going to be talking about the WaterDrop systems and heat pump water heaters in general for multifamily buildings. So WaterDrop Systems was conceived after lots of learning over the last 5 to 7 years with the Advanced Water Heating Initiative in how to transition the market from fossil fuel, boilers and things to heat pumps for all building types. We learned a lot about building types, so we've kind of narrowed down the focus to multifamily buildings, retirement buildings, any building type that really uses a lot of hot water. So high schools with showers are a good fit. And essentially out of that, what we've created is a program where we can deliver a fully functioning, completed skidded water drop to a building. And really, it just needs to be bolted down, 3 water pipes connected, and then we come along and help start it up. There's a product range that we'll take a look at. And essentially what we're trying to create is part of the vision of what we've learned over the years is that building these site-built systems can be complicated. It's got to be designed, it's got to be installed by separate parties, and then there's always a little bit of interpretation along the way. And really, to move a market on a large basis, packaging and pre-manufacturing skids are really where it's at. That's really how we're going to deliver. So as a company, that's what we seek to do. So here's a project that's being set in on the peninsula in the Bay Area right now. There's another water heater that'll land right next to it. All of these water heaters are based on CO2 refrigerant in our system. CO2 refrigerant is really the best tool that we have for domestic hot water. Not so great for space heating or space cooling, but for domestic hot water, it's super good. It's really the best. And the reason that it's best is when you take CO2 and you put it under high pressure, it takes on a high temperature condition, and it actually goes into a transcritical state. And a transcritical state is it's still a gas or a vapor, but it's under such pressure that it really takes on the density of a liquid. So now we have this high temperature, high pressure, highly dense vapor that we can just move along and show to a pipe of water. And essentially that energy just jumps onto that pipe because the pipe really has no energy, it has no heat. And so that transaction happens really very quickly. There's no phase change because it's still in that transcritical state. And so it's a really efficient way of taking ambient air, adding that ambient air across the compression cycle and the refrigeration cycle, and then dropping it onto a water flow. After we've moved that energy onto water flow, the heat pump itself is really going to be managing the leaving water temperature out of the heat pump by varying the speed of the water pump. So that's a way that we can use very little electric energy input and deliver a constant flow of high temperature output in roughly 150-degree leaving water temperature. When we start looking at how we're going to manage these heat pumps and these refrigerants into buildings, we've got new tools. We'll take a look at a new tool called the EcoSizer here in a little bit. But the transition is basically gas boilers have a lot of capacity, right? We just bring more fuel, light it on fire, create energy, and show it to the water, and away we go. And if we need more recovery, we just bring more fuel. Heat pumps are different. We approach system sizing and system application differently. With heat pumps, it's really understanding what that peak load is and designing storage to have enough energy on hand or have enough hot water on hand to serve that load. And then after that, we can start placing and considering recovery rates to resize that load or refill that load. So the transition is really stepping back, looking at the units that we would typically size a plant with differently. Instead of MBH an hour, it's really going to be peak storage, and then adding a recovery rate at a stored temperature, understanding maybe what the incoming water temperature is, what the ambients are, and then creating a package around that. So that's why we're really prepared to deliver a system, because the system that we've designed allows us to look at a building such as this, which is a commercial office tower, downtown Vancouver, 40-year-old building, 34 stories high or something like that. And we're able to convert this building out of gas boilers and into heat pumps. It took about 10 heat pumps or about 45 kilowatts of capacity and a new controller design and new tank designs. And we successfully converted it. And it's working really quite well. Building these site-built systems is something that we've done for years. And we've worked with utilities, we worked with a lot of consulting engineers, and have a method down and sizing tools to accomplish this. But site-built systems are really pretty complicated, and they're not always straightforward to install. Here's an example of a relatively recent project in downtown Seattle. This is a site-built system. This is multifamily housing, and in order to house the plant at the top of the building, then they created this big wooden box, right? Standard framing. So this box has to be designed really just as a mechanical room to hold the heat pump plant. And so design, it's got to be constructed, it's got to be inspected, and then the installer comes in and starts building out a plant. And you can see that the upper right-hand corner picture has got about 5 of these little Senko 2 CO2 heat pumps arranged on top of the building. There's a lot of piping. Each one of those CO2 heat pumps has a disconnect, because we need a disconnect for each one. And then down below inside the room, we've placed primary storage tanks and then a swing tank. And a swing tank is a tank we can kind of talk about more in the in-person events, but it's a tank specially designed to isolate the losses with the recirculation system, so we don't start mixing in that lower return temperature water into the primary storage tank and affect how the heat pumps run. So in any case, it's a lot to lay out. It's a lot of piping to build on site and run electrical and set the expansion tank, set the mixing valve, set the recirculation pump, and start up and maintain. There's a lot of points, a lot of things to consider as we start it up. And so as we start looking at how we're going to scale this business across the needs of the market, it's really quite a challenge. And what we've learned by participating along with the other market players in the Advanced Water Heating Initiative is that the challenge is really to move it away from a craft-based business, which is very much what this is. We're crafting a system building by building and moving it forward into a package system much like this. This is an entire water heater. It's everything, all on board on a steel frame with known seismic values that's capable of just bolting down to the roof of a building or to a slab in a parkade, wherever we want to put it, just like that first picture that we saw. So on board, on the back side, you can kind of see a label that says heat pumps, and tiled across the back of that skid are a number of heat pumps using CO2 as a refrigerant, and they'll take cold water in and lift to 150 and then push that water into that white storage tank in the back, which has got a layer of R12 spray foam. That's primary storage. And then the primary storage will fill with a full 150-degree water. It'll offer that water to that box swing tank there in the middle. And the swing tank is where it goes out of the skid, across the mixing valve, through the out to the building, and then returns through the recirculation pump back into that swing tank. And in that way, we isolate the losses of the recirculation system in the building, and then keep that high temperature water in that white tank in pristine condition, so that we're not sending increasing water temperature out to the entering water temperature of the heat pumps. In any case, it's all piped together, it's all controlled, there's a single power landing, and that's really the concept A of the WaterDrop system. Is everything is completely packaged, ready to go on a skid, and there's a number of skids available. And so we just step back, look at the building need, and match it up with an available skid. When we start looking at site-built systems that are kind of crafted building by building on compared to the skids that we offer, these two plants are very, very similar. This lower plant right here, the blue water heater, is an entire water heater all by itself. It's actually designed and built for an AEA project that we'll be delivering soon with a full M&V system. And those two plants have very similar capacity. The AEA lower unit has a little more heat pump capacity. The upper wood frame building has a little more water storage. But in a peak gallon per day and in a building application, they're really very similar. However, I can assure everybody, and it's no stretch to imagine that those are two different cost propositions. Designing that wood box, constructing that wood box, and then filling it and site installing in that wood box is an entirely different game. So what we do is we've set up a manufacturing facility here in Tumwater, Washington, and then an additional facility in Vancouver, BC, Canada. And we've created an environment where we can just produce these known models one after another. And so here's a project going through the shop right now. And essentially assembling these in a plant is a very efficient way to do it. And we'll start looking at some of the reasons why. One is with this system, we're using multiple heat pumps instead of a single large heat pump. And in cases where you use a single large heat pump, you really have to consider redundancy or backup in case there is some failure in the heat pump. So that means you're adding a large electric resistance tank or adding another large heat pump itself. Over the years, we've all learned that we can depend on these multiple heat pumps, and we can pipe them in a way that if one goes down for whatever reason, the others remain. And that's happened before in buildings. And we found that nobody knew a heat pump was down. It was actually hit in a winter storm by a large tree limb. And no one knew it for a week because the building never ran out of hot water. There was no conditional change. It's just that somebody went outside and saw the damage and knew that there was an issue. So in any case, using this system with multiple heat pumps and building them in a factory offers quite a bit of cost savings. And we're able to set up really simple service by creating three-way valves where each individual heat pump can be valved off. And when it's valved off, there are ports that we connect water pipes, and we can run a descaling operation once a year, twice a year, as often as needed. In those valves, we can also completely valve off the heat pump, depower it, and pull it and replace it in case we need to replace it. However, we can also devalve it, power it down, and lock it out and change a water pump or do whatever service operation we want. It's important to note that CO2 uses high pressure again, 1400 to 1600 PSI in operation, and the refrigeration circuit itself is non-serviceable. It's factory sealed, and I think our company has sold more of these than maybe anybody in the country. And I haven't had I might have had one refrigeration cycle failure in literally thousands of units. So that's not really what kind of where any particular issues pop up. So another optimization is just the piping, the amount of piping that we use, where the piping is placed, the types of fittings that we use. We're able to kind of move them in and make them very efficient, so we're not tying up a lot of floor space to build this plant. Single power landing. So we've designed a panel system with appropriate certifications so that we've got circuits and the ability to provide lockout and additional logic for swing tanks, outlets, lighting. All of these things are kind of all contained in a single plant. And really our role is we want to be really involved in the project, in the water heating side. We're not going to be involved in the structural components or how to build out the distribution system. We're just the water heating company. And rather than trying to match up building requirements with a heat pump and then somebody else's tank, and then whether it needs a brazed plate heat exchanger in the middle and how to control that pump and designing the rest of the system, we offer a water heater. We'll look at the building, we'll size it, we'll work with our local partner with Osborne, have a strong dialogue about the project and how to lay it out. And then when it comes time, we'll make and deliver a water heater, send somebody down after it's attached to the building and spend a day starting it up and looking at everything, including the return temperature across the mixing valves. We've got a really strong presence on the West Coast, manufacturing on both sides of the border, and some really strong partnerships. I'm just super happy about our partnership with Osborne. And as we begin to introduce these markets to these products to the market, and it gives us a chance to talk about new tools. And one of the best tools for multifamily right now is the EcoSizer. The EcoSizer is about 2.5 years old right now. We use it extensively. This is only a partial screenshot, but it gives us a new way of sizing the loads for multifamily buildings and other building types. So this is generally a residential product right now. By just looking at the input level of the building, how many units there are, 1 bedroom, 2 bedroom, 3 bedroom, maybe how we're going to call that occupancy rate, because California's got some very specific occupancy rates, and so we can select that, and we can overwrite our own value or choose a drop-down value. We can look at peak gallons per day. And out of those questions, and then entering kind of the conditions that we're working with, the hot storage temperature and supply temperature and incoming water temperature, type of system it is, and there are a couple more pages where we can really finesse a design, we'll get an output. And the output is simply going to tell us what we need to serve that building or that zone of the building. Because these are water heaters, we can use them in series, right? So we can look at larger buildings, place water heaters anywhere in the building that we want, designed to serve a load of occupants. And when we start breaking these larger buildings into smaller zones, we've got smaller distribution systems, we've got more redundancy across the whole building, we've got smaller pump loads. It's a pretty nice way to look at the building from our perspective. And as we step back, it's always important to kind of look at the relationship of the plant, because this is essentially what we help design or have pre-designed. and apply to the needs of the building. So the first thing is, when we start looking at a multifamily building, we try to understand the peak and really how much primary storage we need to have in our storage temperature of roughly 150 degrees. So once we set that primary storage, then we really move to the left and we start asking ourselves, okay, how much time do we need to recover that primary storage? And the answer to that is to build in increments of 4.5 kilowatts or 15.4 kBTU an hour, and start adding the number of heat pumps or increasing the capacity to meet the recovery time or the recovery demand to service that primary storage. So it's a variable relationship, and we're able to vary that relationship in very small increments compared to larger systems. And then once we establish recovery into primary storage, then we move to the right to the swing tank. And the swing tank sizing, it is its own unique sizing. It's very forgiving. And really it's a question of volume and then how much electric resistance we'll put inside that volume, which will make up for some overnight recovery losses. So we take those designs and we literally turn them into a plant at the shop. This particular plant is going to be storing about 850 gallons with 120 gallons inside the swing tank. And it's got a controller, it's got recirc pump, mixing valve, electronic mixing valve, ECM controlled recirc pump, and everything. It's comes in 2 pieces. It's set on site, and then pipes are joined together to make it work as one. It's got a single power landing for each of those 2 skids. Power landings are actually pretty small. The overall I think on this plant is about 90 amps with maybe 45 in one skid and 35 in the other. We've got a pretty good website with a lot of information on it. We work together with Osborne to take in and understand the building. We can provide some schematics and some submittals and develop a project. And as that project comes to fruition, then we'll send it into production, make the water heater, and then work with Osborne to get it into the market and get it installed and started up. In all cases, it's somebody from our company that comes and does the startup. Lower right-hand corner, we'll share this little link, but it's essentially an interactive, a utility-funded interactive tour of our plant and our facilities. So what it looks like as we build these things, we start with frames, we add water pumps, and we've built out, excuse me, about 7 different models of full skids, ranging from 31 kBTU an hour up to 185. So small to large, and in storage, small to large. We'll work with you to understand really what the building needs or how to divide the building into zones. And they're 100% ready to go. They're pre-engineered. The only question that anyone will really need to answer is what kind of recirculation pump do we need? You know, do we need a small alpha or a large alpha Grundfos pump? You can specify that, because we'll not really understand what the distribution needs and therefore what the pump needs. We'll just adapt our system to fit that pump. Oh, jump the slide there. So as we get into a bigger building, we're just going to add more storage. We'll take that initial basic plant and then add a secondary plant, which is more storage and more heat pump capacity, and build it out into a system that looks just like this. Part load systems are another opportunity where we can offer up a partial load system to an existing building that maybe still has a functioning gas boiler, or into applications where we don't need a recirculation loop, in which case we can pipe directly, mix down from primary and offer it into the building. So it's another opportunity for partial decarbonization or a different application. And then as we get into different buildings, we find that buildings are all maybe a little bit different. Here's a new construction project in California. We caught it in actually after construction, and the desire was to shift from a gas boiler to a heat pump system. So we have a heat pump system where we can actually squeeze the tanks into the small room that is usually designated for a gas boiler, take our heat pump array, same characteristics, place it outside of the building. And we find that this works in many new construction sites that already have a dedicated mechanical room, and we've got some constraints around that, or especially retrofits of all size buildings. We have these droplet heat pump arrays ranging from very small to very, very large. And we're working on one project in Vancouver, BC, where these are serving a very large 62 floor zone, all one zone with these droplet rack heat pump arrays. And the standard product just comes in the same qualifications, and we're just going to be adding this year a couple more sizes on the large end, so we can cover quite some loads and then get them to work together in actual pairs. So we can join them, bring them in smaller pieces, join them on site, and make them work together. All of this is manufactured in our facility in Tumwater, Washington for the US production, which is just a new plant. All it's doing is making water heaters. We've got a fabrication shop, not shown here, and this is a final piping shop where all the products kind of come together. It was named after a researcher who really brought CO2 to North America. And in that plant, we just start assembling skids and piping them all together and working out all the final installation details and QA. We build our own controls, and we have some flexibility in controls and landings, and they're simple to place and connect. Jumper piping, clearly labeled, low voltage control boxes when we're joining two skids together, a really strong QA process performed by production and systems engineering. As the final step, those beams are actually hiding a pick point, and we've got steel 3/4 inch pick point eyelets on the top of those things, and those are about to go out and get strapped down onto a truck, and so those beams are going to carry those strands. Small water heaters are delivered on small trucks. Big water heaters are delivered on big trucks. And that's a project heading down to California there a few weeks ago. Looks a little bit colder than it is today here in Olympia. And then it's all followed by startup. Startup includes looking at the return temperatures across the recirculation loop. And this is where we hope to meet people soon. This is the live event. We'll be taking one of these full-size skids down through California and working through the Bay Area. So Brian is sharing the link out, and I just look forward to meeting anybody at the live event. With that, I'm going to let some other folks have some time to talk.
Real quick, Albert, just as you can chime in on this. In your experience, footprint-wise compared to a gas system, on new construction, I'm assuming the footprints can be a little bit larger just because of the storage, but on retrofit, you may actually be similar or smaller because your piping's probably going to be better.
So, retrofit, so in all cases, transitioning from a water heater or from gas boiler to a water heater, the footprint's going to be bigger. The boilers really don't need the storage. They just have high recovery. So the limiting factor is really always the water storage. Once we can work the water storage out, then typically we can find a place somewhere to rack the heat pumps and place them away in that droplet program. So that's where we get out of the skid concept and work with maybe a semi-assembled concept where we're delivering racked water heaters, all the controls, power landing, and then delivering the tanks that can be placed and piped by the installer. Does that make sense?
Oh, yeah, okay. I do have a couple questions, but I'm going to hold off on them. One of them I think I can answer on my own. So next up is going to be John, as long as he's still with us, which I assume he is. So John, you should be able to just start sharing.
Right, folks see those slides here? Great.
Yep, you're good to go, John.
Cool. Yeah, my name's John Neal. I'm with the Association for Energy Affordability. We're a nonprofit technical services and consulting firm. We have an office in New York and a strong presence in California. We primarily work in multifamily buildings. We sometimes get involved in some commercial projects, but a lot of what we do is centered around delivering energy efficiency, decarbonization, and renewable energy programs for multifamily buildings. And sort of at that intersection, we also end up doing research and development projects. We get involved in policy, and we are also involved in trainings as well. Just wanted to give you a quick snapshot of what the landscape looks like for incentives for heat pump water heating systems in California. This is a list of just the programs that AEA is involved with in California for multifamily buildings. All of them have incentives for heat pump water heating systems, except for this top one, which is solar PV focused. Don't have enough time today to talk about the ins and outs of all the different programs, but I just want to sort of underline and emphasize that all the programs that are really running up and running today, incentive programs, are focused on decarbonizing buildings. There may be a few legacy programs that will still sort of incentivize gas-based systems, but this is sort of where things are at now, and the money is pretty significant. I've sort of highlighted a couple programs in red that are sort of going to launch either just like yesterday. The California Electric Homes program launched. That's for new construction, market rate multifamily. And then this other program, the self-generation incentive program, is launching later this year. And folks might be familiar with that program related to batteries. It's primarily been a battery energy storage program. It's going to be available for heat pump water heating, thermal energy storage later this year. So AEA has been involved in central heat pump water heating systems for quite a while now, and sort of through that process, we've really gotten to see, I think the spread of products that are generally available domestically for water heating. So this is sort of the list of products that we've been able to sort of work with, and they all have different pros and cons and applications that work well. The Sanco system over here uses the same sort of compressor that Albert was showing previously, that's used for the WaterDrop product. Wanted to spend a little bit of time talking about some of the research and development we're doing, because it sort of overlays one of our demonstration projects is using the WaterDrop system. So these are some projects we have actively running right now. And this upper one in the upper left is focused on large capacity, low global warming potential refrigerant heat pump water heating systems. So we're sort of focused on using CO2. That project is really focused on larger scale plants. We're using the Mitsubishi QHV system and the WaterDrop system in our demos for this project, which is funded in part through primarily through the California Energy Commission, and our demos are also getting some supplemental funds from some other sources as well across the state. That team includes Ecotope as the primary engineering lead. Mitsubishi is involved for the Mitsubishi QHV equipment, and then NBI and AWHI are also on our team. And Mischa, who's coming just after me, we'll talk a little bit about that as well. This is a snapshot of our demonstration projects. I'm going to just sort of click through and show you what those are starting to look like in case they're interesting to folks. But it's sort of a range of climate zones, installation locations, and then sort of based on the existing projects, a range of sort of capacity and storage to recovery ratios. This is a quick shot of our first QAHV project. That's Mitsubishi's large capacity water heaters in San Francisco. Project is up and running. M&V has been ongoing, and we're just starting to sort of collect the data and sort of parse through it to get an idea of how well that system is working. And an upcoming test that we're going to be working on is, while it's not a standard design, we're interested in seeing if the equipment can manage recirculation load in the building instead of running it through a swing tank. And then just to compare against sort of what Albert was showing previously with site-built systems, you can sort of see at the bottom of the image here what the boiler room looks like. This is basically all the equipment you see in this photo is dedicated to the water heating system. Our WaterDrop demonstration site is in Fresno. This is a shot of the building. It's a 106-unit building, and it's split into sort of two wings. It's two boiler plants existing. And one of the reasons we looked at using the WaterDrop was the areas right outside those boiler rooms were really visible to all of the apartments. The boiler rooms themselves were sort of limited in terms of space, and adding additional storage without triggering a lot of structural work to support additional tanks. And the roof had sort of the same issue. We didn't really want to have maintenance teams having to go up onto the roof or having to deal with that structural work. And so we found two locations to put the skids outside that will be generally away from apartment views. And the contractor that is going to be installing this had sort of two routing options for the piping. One was through the attic of the building to the existing boiler room, and the other was to run exterior. And they are actually looking at using sort of a trenching-based approach to connect the water lines to the existing boiler plant. So this site was a great fit for these skids. We have a lot of space. It's not a dense urban environment, and we're excited to work on this project. It's going to be starting here next month. Albert covered most of the sort of advantages of CO2, so I don't need to sort of spend a lot of time on this. The one thing I'm going to mention at the bottom, this doesn't, I think, have anything to do with CO2. But I will say that one thing that we're really excited about with the Sanco equipment, WaterDrop systems, and the Mitsubishi equipment as well, is that the equipment is really quiet. I think probably this is more of a function of how well they're engineered, but they have been really useful in using these systems in our projects in like the more dense urban environment where we have to meet noise ordinances or be sensitive to the residents that live in the building. And I did want to make a case for factory built. You saw that picture I showed of the boiler room. We've been involved in a lot of central water heating systems, and I will say they are all somewhat bespoke. Even when they're repetitive and a contractor is building one after another, mistakes can happen in the field, and that can sort of take a while to unravel and fix. And moving to a factory-based solution really has a great potential to sort of standardize the work product. We are using the WaterDrop project, or excuse me, equipment now for sites that we have maybe some flexible space. So we're not obviously like taking over a boiler room and taking the WaterDrop skid and sort of putting it in the boiler room, but we are looking for locations that maybe have a back of house or some landscaping areas. Parking garages are a good site application for that WaterDrop. Obviously, all new construction projects are pretty easy to sort of fit that system in. And we've just started using the droplet for sites where maybe we don't have a lot of space, but we can sort of look at using that rack basically on the outside of the building, or we can usually find ways to sort of fit that in pretty easily, and then go with sort of standard site-built storage solution inside an existing boiler room. And yeah, Albert covered the sort of redundancy note, but that is something that we're running into as well. One of the benefits of this sort of droplet system is having multiple heat pumps, a little bit more redundancy, especially as you get into larger buildings where maybe you could serve the load with one large heat pump, but duplicating that heat pump in an existing building would consume more space and a lot more of electrical capacity. So we sort of navigate around that a little bit by having lots of sort of smaller heat pumps. I'm going to cut it here and give time back to Mischa to go through her slides, and then we can cover some questions at the end, if any come up.
Thanks, John. All right, give me just a moment and I'll get my screen share going.
Yeah, I'll let you know once we can see it for you.
Thank you.
All right, you're all good to go.
My name is Technical Associate at New Buildings Institute. We're a nonprofit and we coordinate the Advanced Water Heating Initiative. So that is a collaborative group. We have over 140 organizations participating, working together. I mean, I think the key takeaway is just trying to accelerate the adoption of efficient, grid-connected, low global warming potential heat pump water heaters. And we do have some ambitious goals, but we have a really great group of folks that are working together on them. We have a few different working groups, and the most relevant for this group is the commercial working group. We have 3 leads representing kind of the utility side of things with Kashmir McVeigh from the Bonneville Power Administration, John Heller from Ecotope on the engineering side, and then Helen Townsend from DNR International. That virtual tour that Albert mentioned, the DNR is the one who put that together, and it's a really great resource. So that kind of education and outreach is covered there. So really kind of trying to hit all the different pillars for market transformation. So there's a lot on this slide, but basically just reiterating what both Albert and John have already hit on about how important heat pump water heater systems are to some of the issues that we're facing in terms of decarbonization and energy efficiency. I think the key takeaway here is that, you know, we all know that domestic hot water systems can account for a fair amount of building energy use, especially in like multifamily buildings. Ecotope has done a lot of studies on how transitioning to a heat pump water heater can save a lot of energy. That pie chart is just an example of one of their studies. The other thing that's really important that I'm not sure that we talked about too much from the other presenters is just how heat pump water heaters can contribute to grid stability. Basically, because they have all of this hot water storage, they act like a giant thermal battery. So this is a really good resource for folks, especially in California, to have when there's a demand response event. So then with the communication capabilities that can integrate with the demand response programs, and it can help save money and also provide some resilience in case of an outage. So I also will just briefly mention that, you know, there are a lot of upcoming, people are looking at heat pump water heaters and how to integrate them into codes and policies. Seattle is one example. I know it's not in California, but they do require all multifamily and hotels, motels to use a air source heat pump water heater for domestic hot water heating. So we're expecting that we're going to start seeing more of that. So it's good, whether you agree with it or not, it's good to at least know what may be coming in the future. So I just want to quickly kind of go through some of the important parts of, you know, again, what the AWHI group, different members of the AWHI group have been doing to really try to help scale these systems. So there's 4 components. I'm going to just quickly go through each one of them here. The first is the advanced water heater specification. This is put out by NEA, the Northwest Energy Efficiency Alliance. It defines minimum performance criteria and test protocol specifications for central heat pump water heaters. They also have an advanced water heating specification, you know, for just like residential water heaters, just like little unitary water heaters, but it has been expanded to commercial systems as well. So the goal is really to ensure that the performance of these systems is repeatable and reliable and provide a public resource for folks to know that there is uniform testing happening, they define a system COP, which I'll talk about here in a little bit. But I've got a link here, and just good to know that, you know, this exists, this specification that kind of provides guidelines on how to quantify the performance of these systems. The other kind of step in this process is the product assessment documentation sheet, PADS. And so really the goal of this is just required by manufacturers to measure their performance. I think Albert talked a little bit about the EcoSizer tool. There's also a tool called EcoSim, helping kind of model these systems. And the goal of this is to really help define and guide best practices for designers that are looking to use this equipment, provide a little bit more detailed information on that. So just quickly wanted to mention that EcoSim tool that I was describing. It's a simulation tool, and so it's going to model the system COP. So the COP number that you get for your system is going to depend on if you're looking at just the compressor or the entire system. So again, the advanced water heating specification provides some guidelines on how to get that number and come up with this uniform system COP. It utilizes that PADS document that I referred to and the performance map as inputs to the modeling. The EcoSim models 4 climate zones for different prototype buildings. You can see some examples here. And then there's also a sensitivity analysis. The takeaway is it's very robust, very technical, uses a lot of good specification inputs to come up with this performance number that people can really be confident about. So then the last resource that I wanted to mention that's really trying to help drive greater awareness in the market is the qualified products list. So this is kind of the culmination of all of those things I was just describing. This is the public facing documentation of which products have complied with the advanced water heating specification. So you can see this is just a screenshot, but it has that modeled system COP. It provides that for 4 different climate zones. So like not specific climate zones, but, you know, hot, mild, cold, very cold, just so you can see how that impacts the performance. And the goal of this qualified products list is to be referenced by utilities or code officials for compliance or incentive programs, and also for designers and consultants to help kind of understand the performance of different options. So I also just wanted to mention, since this is a California-focused event, there are, so in 2022, there was a prescriptive compliance pathway created for central heat pump water heaters in the code. Changes are being proposed for the next code cycle that would require infrastructure enabling a future retrofit to the central heat pump water heaters in new multifamily buildings that are being installed with centralized gas water heaters. So this is information that was shared at one of our commercial working group meetings. So again, just a plug, if you're interested in this kind of stuff, might be worth joining that group so that you can stay in the loop. Feel free to reach out if you have more questions about that, but I'll spare you all any more details on that. I just wanted to hit again that interactive virtual tour and some more great work being done by DNR International. They have this, they also have tours of actual like buildings where these things have been installed. I think that they're getting ready to do one for the WaterDrop system. I'm not sure that they have one yet, but I would definitely recommend checking that out. Okay, so I gave you all kind of an overview of what's happening with the Advanced Water Heating Initiative, some resources to know about. I also wanted to just quickly talk about some research that NBI did as part of that large capacity CO2 project that John was describing. So he talked about that. I'll just give a shout out, appreciate being on the project team with AEA. And our work was also joint funded by NIA. So it has kind of like a little bit of a spin for the Northwest market as well. So we conducted research last year trying to understand the primary barriers for central heat pump water heater adoption, specifically in multifamily buildings, and trying to understand what's driving the market right now and how we could increase adoption. We did a scan of the existing literature. We talked to a lot of experts. We did an online survey where we got 34 responses, mostly from the design community. And then we did 29 interviews, trying to balance all the way through the supply chain, from manufacturers down to facility managers, end users. So just what we found in terms of the primary barrier, just for these folks, and maybe some of you can relate to this, installation complexity was the number one barrier that we identified. And so that's part of why this WaterDrop system is so great. I know we've all been talking about it, but we really are seeing, feedback from the market that this is a challenge. And the lack of installer education or awareness, makes that even more challenging and can increase the upfront cost. And then that paired with just workforce shortages, or just lack of interest, can really jeopardize these systems being selected at all. So I wanted to just do a little bit more of a deep dive into just one of these, which is just to say, we spoke with a really great facilities manager who said these systems are like a car. You need to know how to change the oil and do basic maintenance, but then you just need to know who to call for the more involved issues. So I'm not going to read through this slide for the sake of time, but just trying to keep in mind who's actually going to be using these systems. And I think that, the WaterDrop system helps make some of these barriers that we saw a little bit easier. So why are people selecting central heat pump water heaters now? The number one reason is incentives, by far. Most people said this wouldn't have been possible without incentives. So what John was saying about all the programs available in California, definitely encourage you to be aware of those and take advantage of those wherever possible. But something that I also wanted to point out that might be helpful for this group, I'm not sure where everyone's coming from today, but I imagine there might be some designers in the group or folks who have been on a project team. There were quite a few folks we interviewed that said influence from the project team was kind of the deciding factor. So even though this is only, 4 mentions, it was kind of like a big deal for the people who mentioned it. So just wanted to keep that in mind, that if you're someone who's passionate about this type of product or pursuing this, don't be afraid to speak up, because that might really make the difference. So based on our interviews and our survey, we have kind of 4 high-level recommendations for the market about how to improve the awareness and adoption of this equipment. The first is trying to share best practices. So events like this are great, trying to get everyone together and spread the word. Workforce education and training and awareness building is also really important. Access to performance data is something we recognize is something that everyone wants. So projects like what AEA is doing in California with the WaterDrop install and the Mitsubishi units is really helpful. It really helps to build confidence. And then also developing packaged systems. They really simplify the design process. And, we also identified that it's important to have cost comparison tools. I think Albert is the one who actually shared this with us, that, we want to make sure that we're really being able to do an apples to apples comparison. So we're really trying to focus on that. A few lessons learned from successful central heat pump water heater projects for everybody to consider. There are a lot of trades involved in these projects often. You know, the WaterDrop system helps kind of ease some of that, but it can be a big project team. So we heard that early coordination and communication is just really important. Getting the architect on board early, the installers, and communicating also with the utility and the city officials too, just to see if there's going to be any issues there. The project delivery method, so design, build versus plan spec, can impact the contractor's sense of responsibility and investment in the project. And also a few folks mentioned that working with more specialized consultants, like a domestic hot water consultant or a commissioning consultant, which again shouldn't be as much of an issue with the WaterDrop, but for some of the other more complex systems, that can be an issue. And so just spending the money to have someone who really knows their stuff can be worth it. Okay, so I think that we've pretty much beat this to death. We definitely want to promote this package system. And I think that one of the gaps that we identified that I haven't mentioned previously is just trying to understand the market potential. We recognize that as an area of future research. So resources, if you want more information about the research that we did about what's kind of driving the market, what the barriers are, what we recommend to deal with those barriers, I have a link in my slides for the full report. I have a link here for the commercial working group if you're interested in keeping track of what's going on there. Ecotope created the CO2 heat pump water heater quick design guide as part of the project that we're on with AEA. It's a really helpful quick kind of cheat sheet. It's more focused on the Mitsubishi product, but still some good stuff in there. The EcoSizer tool, which Albert mentioned, and also the AWHI resources page has lots of other reports and good stuff for all things central heat pump water heating. So I gave us 3 minutes to spare, Brian.
No, did a very nice job. Just because we are going to answer some questions really quickly, we're going to start losing people immediately as soon as one hits. So I just want to say thank you really quick to everyone that's here. We are going to be answering some questions, so feel free to stay on with us. But I just wanted to, like I said, say thank you to everyone that has attended. So looks like Albert's really the one that's up on the questions. Someone did ask if I'm going to share the slides. I will get a PDF version from everyone so that you guys have any links that were in there and you have those to reference. So that'll get sent out to everyone. One question that popped up in my head, Albert, was, I know we asked about it, but I wanted to get your answer to it, was the seismic requirements because of California. And if you could just touch on that, if there's anything special done to it already for that.
Yeah, so everything in our product line are built on one or two frames for a full skid approach, and then the droplets are on a rack system. All of them have had seismic calculations done, and done in a way that meets California requirements. Also, up and down the West Coast too. So we're taking that approach. We've got full submittal drawings. We can share all the calculations. I don't know at this point if we've got a stamped frame drawing for California, but that's probably on our work list. So there's a simple pathway to meet any of those seismic requirements.
Another question that came in, this was more about sizing around kitchens. So commercial kitchen, high temp water. And if you guys have the understanding that would be required to, size in that type of application.
That one actually just came up on a regional technical forum discussion yesterday, was commercial kitchens. So yes, we're working with 150 degrees. So depending on what's required, we can work that. It's a question of, storage and really kind of what the water use cycles are. CO2 in some circumstances, CO2 in a classic primary storage swing tank is going to be a suitable application. And in others, some of these newer unitary 120 gallon commercial water heaters might actually be a better tool because they'll dump some of that. They're a little smaller, maybe a little higher recovery, dump some of that cooling. So it's a bit situational.
Another one that came in, because I know our restraint on this one when it comes to water source heat pumps versus air source heat pumps is the cost to actually drill the ground, to put this back into the earth versus putting it into the air. But Victor had a great question. Do you guys have anything that may be able to take care of waste heat? I know that's a really specific market right now, but waste heat recovery.
Yeah, we don't have anything. However, the one application I can say, this was done with essentially the original droplet category where it's racked heat pumps in that Vancouver, BC building that I showed today. The heat pumps were placed up on the top floor. There was tons and tons of, literally tons of waste heat that all went into the domestic hot water. So into the air source heat pump, and then into the primary storage tank. That's about as close as we as a company can get right now.
Yeah, using that exhaust weight piece that's coming in. There was one other one. I think Ashley typed your answer in on for that one. We talked about controls. So Ashley put that in there just in case people didn't see it. There is Modbus is your standard platform, but he put in there that you can have a BACnet BMS communication upgrade, remote monitoring module, and either through Ethernet or Wi-Fi or cellular, right? So that you have that. So if you don't have a BMS system, you can still have some type of visual to it.
Correct. Yeah, and there's lots of really interesting things coming later this year with controls, which is also the EcoPort, which will then qualify a plant for the SGIP program. So that's basic demand response, and that'll be a standard product in the WaterDrop product list. Along with, we're planning a full M&V kit with every product as standard. So it'll calculate a site-based system COP, maybe, and we think it's including the recirculation system, although we'll probably get some dinged. We'll get dinged for losses on the heat loss in the recirculation system, but we'll have some level of a standard M&V kit as a standard feature.
And then I really wanted to comment on this question just because of the way it was written. I just did a recent presentation talking about heat pump water heaters and high temp storage and then mixing valves for residential. So some people they hear swing tank and they hear electric element and they're not quite sure what that actually is. And because in a lot of heat pumps that use a different refrigerant, they become inefficient at 37 degrees. So when the ambient air goes below that, they have electric elements because electric COP is basically 100% one. So if your unit becomes less efficient than the electric, they'll have an element to take over, right? That is not what the swing tank is.
It's not what the swing tank is. So two things. John's chart, John showed a COP over ambient temperatures. And the other reason we love CO2 is it works in really cold ambience. We can use it anywhere in California. And boy, we can go way north. And it'll work in all conditions, deliver the same output, high temperature water, and maybe just lose a little bit of capacity and flow. So that's great. And so, we can see all the way down to -15. And we're still producing a 1.75 COP, right? -15F, 1.75. No other refrigerant's really going to work with us to do that in that capacity. Swing tank's a different thing. Swing tank is, in order for that CO2 refrigerant to work, it's a relationship of an inverter drive, variable speed compressor, variable speed water pump, and it's all triggered around, kind of standard entering water temperatures, and it's tuned to take that entering water temperature, lift it 100 degrees, and then deliver it out. When you start getting rising water temperatures, like in a primary storage system, where you have recirc coming back in and mixing with that 50 degree or 48 degree cold water, and that starts showing up in the heat pump Heat pumps aren't really set to do that. They can only speed up the water pump so fast, and they can only slow down the compressor so slow, and then they just start struggling. So the swing tank is basically taking that recirculation, placing it away from primary storage, giving the building the recirculation, or giving the building the 150-degree water out of that swing tank, sending it across the mixing valve, mix it down, send it out to the building, get a flow back at maybe 10 degrees cooler, and then isolate that return flow of 110 degrees or something of that away from the tank full of 150, so we don't start mixing that 150-degree water. And it's literally called a swing tank because the temperature in the tank will swing high when there's flow through it, and we get a constant flow of 150, and it'll swing low when it's an overnight condition and there's no flow through the tank. So then we're sending it out 150 out, mixing it down to 120, out to the building, return at 110. Sooner or later, that activity is going to reduce the entire storage volume and lower that temperature. So at the bottom of that tank, we just throw in 6 kilowatt, 9 kilowatt, 15 kilowatt, whatever the recovery loss is on that recirculation loop. We just throw a small amount of electric resistance in the bottom of that tank to make up for that loss, so that when it approaches that mixed temperature, electric resistance fires on, does a lift, and it only does a little bit of a lift until there's flow in the building and more 150-degree water comes in and populates that tank to full temperature. That's the swing tank, and it just swings high and low based on what the flow is.
Yeah, so when you see electric elements in other units that cannot go as low as a CO2 refrigerant can, theirs is a true backup electric element.
Because of ambience.
Because
and
of ambient
inability of the refrigerant to operate in the cold ambience. Yeah.
Yeah, it's one of those things, you know, has the technology advanced even in the gas? You had gas where the inlet water temperature did become a problem because you wanted condensation, right? So we already learned that we want the coldest water in. And now the new technology throws one other wrench into it, and it's ambient air, because the ambient air and the return water temperature both affects efficiency. And that's why you have this swing tank design. So you've just added another element to the efficiency compact.
Yeah, and that's when we step back and we just don't look at a heat pump, we look at an entire plant. And the plant is the relationship of high temperature storage to the recirculation system. So that's a plant view rather than just a heat pump view. And can my heat pump operate at 32 degrees Fahrenheit?
Yep. Just because we are talking about lower temperatures, and I haven't heard anything about this, I'm actually kind of surprised no one asked. Is there a defrost cycle on the samples?
Yeah, the sample tubes that we use actually use a hot gas bypass. So there's no classic reverse cycle or reversing valve. In a hot gas bypass, essentially the system, when it's up and running in a mid-level ambient, 50 degrees to 60 degrees, something like that, it's taking the ambient energy, putting it into the air side coil, giving it to the compression cycle, and then giving it to the water pipe. And that water pipe is going to be pushing through maybe 0.3 gallons a minute. In a defrost condition, when we have lower ambient temperatures, the water pump will probably slow down a little bit, or maybe the compressor will speed up and make up for that gap. But what'll happen is when it goes into defrost to burn the ice off of the back of the air side coil, it'll take a little refrigerant and send it over across this coil. Meanwhile, we still have full temperature water. We still have a full refrigeration cycle creating that heat and showing it to that water pipe. That water pipe, because it's got a little less available energy across the refrigeration cycle, the pump will probably slow down and will just produce a smaller flow rate of 150-degree water during a defrost. So in our systems right now, there's not a large defrost penalty in cold ambience. There's a number. It's a very, very small number, and it's a question of whether it actually gets used or not, because you got to be in some really cold ambience before that is really a factor in CO2. Other refrigerants, definitely a factor. CO2, different animal because of that transcritical state.
Yep. And the last question, Victor, I'm not quite sure if I'm answering this correctly. He was referring to for CO2 heat pumps, COP is relatively high at cold ambient temperatures compared to a different refrigerant. But then he wrote, but is HP, I'm not sure if he's referring to horsepower or heat pump output capacity consistent at low ambient temperatures as well, or does it drop off? So I'm thinking he's talking about recovery rate.
So it is, if John threw that slide up again, what we're going to see at -14.
Thank you, John.
So see in that blue line up there, that's the capacity dip. And the capacity dip starts less than 12F. And we go from 4.5 system capacity down to 4.25, 4.2. So there is an effect, and we can factor that effect in. But again, CO2, and you really think about it, it's at that -14 condition, it's not taking a lot of energy out of the ambient, or it really considers that -14 ambient as a useful contribution, right? So it's going to expand the refrigerant back to a thin temperature that's a lot colder than -14. So it'll gather that energy in, but it's still within the parameters of the operation of the compressor and the water pump and the fan. It can still deliver that full temperature with a slightly smaller system capacity based on, a little bit slower flow rates.
Just because this came up and you said this to me earlier, because I had a question.
Yeah.
This is what basically what we're kind of showing is the ambient air is going to have an impact, but you can see how much more detrimental to the COP a higher return water temperature is.
Yeah, for sure.
Granted, this chart has to be a fixed ambient air temperature, going through that. But I thought this was quite impressive that you're talking. Yeah, this is why you don't want 110 degree water.
I think if you slow down, one slide down, if anybody's really interested. Okay, so on our little manufacturing building, there's a smiling face of a guy that lived here in Olympia who did all the initial research around CO2 for water heating in North America. And this is a chart that we all discovered together when we're trying to use CO2 for space heating. And you can see that red line or the green line at the bottom is the incoming water temperature. And as that starts increasing, then the capacity, the blue line at the top, starts dropping. And the water flow rate starts increasing to make up for the incoming water temperature, right? Because we always have a fixed finish temperature. So as we get an increase incoming water temperature, we have to speed up the water flow because the refrigerant is we can only slow the compressor down so much, right? And so we still got all that energy and we can only push the water so fast. And this is really indicative of CO2. Generally, the CO2 products that we have in North America right now are great at lifting water at 100 degrees Fahrenheit in a single whack.
Yeah.
They're really not good at space heating or space cooling. They can do freezing well. Just currently right now in Europe, there's been some progress in doing some space heating and cooling with CO2, but it's a different animal than the water heating equipment that we're working with now.
Okay, so yeah, just because that came up. So that's all the questions and everything that came up. Oh, there we go. Stop sharing. Move my button around. I do want to be cautious now of John and Mischa's time also, because they've been gracious enough to sit in just in case anything popped up. So that's everything that we have. There will be a recording. I will send out a copy of each presentation all combined into one, so that if there's any links or any information you guys want on that. If there's any questions that any of you guys have, you'll have the contact information for the group. So for Mischa and John, if you have it directly, or for Albert or us, if it's more on the equipment side, I'll make sure I get that all to you. And I just want to say thank you again for everyone, to share your knowledge with us. And I'm glad that this worked out as well as it did. Thank you guys very much.
Thank you. Been a pleasure.
Thanks, everybody.
Thanks, Mischa. Great to see you again.
Yeah, everyone enjoy your day.